Assalamualaikum and hi everyone. My name is Izzah binti MOHD and my group mates are RAHAIZAN binti Abdul Rahim and IYLIA binti Mohamed RAZIB. We are from Group O Part 4 of Faculty of Applied Science. So today's presentation is about Franck-Hertz Experiment. Let's start with the introduction. Introduction. James Franck and Gustav Hertz conducted an experiment in 1914 which demonstrated the existence of excited state in mercury atoms, helping to confirm the prediction of quantum theory which predicted that electrons occupy only discrete, quantized energy states. This experiment supports Bohr model of atom. For this great invention, they have been awarded Nobel Prize in Physics in the year 1925. Okay, next, the aim of this experiment is to experimentally demonstrate the concept of quantization of energy levels according to Bohr's model of atom. There are some apparatus that have been set up in the Franck-Hertz experiment, which are power supply, tube, which is discharge tube that containing low gas pressure, and 3 electrodes. Number 1, cathode that used for emissions. Second, mesh grid which is used for the acceleration of electrons, and the collecting plate. Figure 1 shows the schematic diagram of Franck-Hertz experiments. So how this experiment work? Well, now I will tell you guys about this experiment. First, with the help of thermionic emission, electrons are emitted by a heated cathode and then accelerated toward the mesh grid. The mesh grid is at positive terminal relative to the cathode. Second, the collecting plate is at lower potential and it is negative with respect to the mesh grid. If the electron have sufficient energy on reaching the grid, some will pass through the grid and reach collecting plate, and the electrons will be measured as current by emitter. Meanwhile, electrons which do not have sufficient energy on reaching the grid will be slowed down and will fall back to the grid. As long as the electron collision is elastic, the electron will not lose energy on colliding with the gas molecule in the tube. As the accelerating potential increases, the current also increases. But as the accelerating potential reaches a particular value, which is 4.9 electron volt for mercury and 19 electron volt for neon, each electron possesses that much of potential, and now the collision becomes inelastic. Now, the electron almost loses its energy and measured current drops.
So, I will continue the explanation on data for mercury. On the left side of the slide shows the graph of collected current versus accelerating voltage. First, when the accelerating voltage reaches 4.9 eV, the current drops sharply. 4.9 eV is the lowest energy required by the mercury atom for excitation. This current drop is due to inelastic collision between the accelerated electron and electron in the mercury atom. This suggests that the mercury electron cannot accept energy until it reaches the threshold to elevate them to an excited state. Next, collected current drops at multiple of 4.9 eV. At 9.8 eV, each accelerated electron gets sufficient energy to participate in 2 inelastic collisions. They excite 2 mercury atoms and no energy will be left. Lastly, this process will repeat for each interval of 4.9 eV. Data for neon. First, when the accelerated electrons excite the electron in neon to upper states, they de-excite in such a way as to produce a visible glow in the gas region in which the excitation is taking place. There are about 10 excited levels in the range 18.3 to 19.5 eV. They de-excite by dropping to lower states at 16.57 and 16.79 eV. This energy difference gives light in the visible range. Lastly, if the accelerating voltage is high enough, they can undergo a series of reactions by the inelastic collision between electrons and neon gas. So, that is all from us. Thank you for watching.